Now, similar to the mechanical hydraulic, the equivalent in resistors and water hoses, we can represent an inductor through a water mill. Like in a water mill, the inductor current, or the water current, cannot abruptly change. So you cannot stop the current flowing through a water mill. If you would try to stop the water mill, like putting a stick or any other blockade into it, either the inductor or this, so the water mill, or the stick would break. So the current, the electrical current in an inductor or the water current in the water mill cannot make any jumps. If you make jumps on the voltage, on the water pressure, on the other hand, the current would not increase immediately, but would be delayed, and then inertia, the existing inertia of the water mill or the existing current of the inductor would slowly ramp up. Now, looking at the physical laws behind inductor, we have Faraday's induction law and we have Ampere's law. Both of them are built on Ørstel's discovery of the electromagnetism. Faraday's induction law tells us that the number of turns times the magnetic flux is equal to the integral of the voltage over time of that inductor. And the definition of the magnetic flux density, B, which is a vector, therefore the arrow on top of it, is the magnetic flux defined by an arrow, as every density is related to a geometrical size. And here the effective area is the effective cross-section of the magnetic field. Putting in the equation 17 from above here, we have the integral of voltage over time up here, and we divide by n and the effective cross-section of that magnetic field. Rearranging it so we get the voltage out of Faraday's induction law looks like equation 19 here. Now, as we derive the voltage, we also need the current, and then through Ohm's law, we can combine those two. We can get the current from Ampere's law. If we multiply the number of turns with the current, we have on the other side of the equation through Ampere's law the integral from 0 all the way up to the length of the magnetic field, the effective length of the magnetic field over the length. That means, rearranging this one here, we can, from equation 20, derive an expression for the current in the inductor. Now, applying Ohm's law on the inductor, we have the integral of the voltage over time on the numerator, and we divide by the current, which we've just seen in the previous slides. Taking in the equations from the previous slide, so this is the equation for the voltage over an inductor that we derived from Faraday's law, and then this one is the equation for the current in an inductor derived from Ampere's law, can be simplified over here to n squared, which is the number of turns that we have. So the number of turns a conductor is wound around the magnetic field, the effective cross-section of the magnetic field, and down here the integral from 0 to the effective length of that magnetic field, as an integral of the magnetic field over the length. So going all the way around the magnetic field path until it's closed. There are no magnetic monopoles, as we know from Maxwell's law. So all the magnetic field lines have to be closed, and the path these magnetic fields are taking is our integration way L. We have the magnetic flux density left as the numerator of that equation. Now, when we constrain the material to be homogeneous and linear, that means that the magnetic attributes along that magnetic field path is never changing. It has always the same attributes along the way. We can turn the integral down here into a simple multiplication of the magnetic field times the effective length. The first part of the inductor equation here is, again, as we've seen also with the resistor, material dependent. So B divided by H here is a material dependency, also called the permeability mu. And the other two factors, the effective length and the effective cross-section, are geometrical values, and those two are describing the field, the magnetic field, and the path of it. So those are geometric. And N is just simply the number of turns of the conductor around that magnetic field. In practical engineering use, the material and the geometry are very often coupled together, as we are trying to buy some ready-made cores which have a given dimension, can be smaller, can be bigger, but depending on which core you have, the magnetic field path is fixed as you try to convey the magnetic field inside that core, and the material is also given by the material this magnetic core is built of. So for engineering dimensioning practices, we can put all of these values together into a so-called AL value, and compared to what many physics textbooks are using, that is 1 over the magnetic resistivity of a core. So the AL value is 1 over the magnetic resistivity. Summing up those equations and rewriting them, we can simplify the inductance to AL times N squared. Applying a DC voltage across an inductor would lead to this integral here being integrated over time until infinity, because the DC value will stay constant forever. And that means that the current would follow that path of the integral, and as the integral is going towards infinity, means that the inductor current would also go towards infinity, which is theoretically possible, but practically that would lead in some destruction of either the inductor or some other parts of the circuits. Therefore, it is never a good idea to apply a DC voltage across an inductor, or the integral from 0 until infinity over a voltage across the inductor has to be 0. Now, looking at the instantaneous energy of an inductor is equals to the integral of the instantaneous voltage across that inductor times the current flowing that inductor over time. We can rewrite that equation by applying Ohm's law, as we've just used it on the previous slides, taking the inductance itself outside the integral, assuming that the inductance will not change with time. There are effects like aging and things like that, but in the first approximation, it is a very good assumption that the inductance will stay constant across that integral here. That would mean that the voltage across the inductor turns into the derivative of the current times the inductance, which we put outside the integral, and we have the current left here from our previous definition of the power inside that integral. Now, this is a rather unhandy integral, as the function inside the integral is not really easy to solve. But there is a mathematical method called the partial integration of the x times the derivative of x inside an integral results into x squared minus the original integral that we tried to derive. And as this is an equation, we can simply fold the last integral over to the other side, and therefore we have a solution for x squared. As we wanted to derive a solution for the energy of the inductor in the first place, which is the integral over here times the inductance here, and our x from down here is the same as the current from up here, the inductor current. We can simply place the inductor current from up here into the equation down here, and that means we have a solution for our energy at the end, where the factor of a half is coming from the solution of the integral being set in here. And the original contents of the integral, which was our inductor current times the derivative of the inductor current, shows up as the inductor current squared over here. And the inductance L, which was outside the integral, we will keep along the way and just multiply with the result of the integral above. That gives us the final equation on the inductor energy, which is defined at any instance of time. So we can just have a look at that at any time during the signal and always relate a specific amount of energy stored in the inductor at that specific time. Ideally, an inductor looks like the symbol itself just being an inductance. Practically, and as a first approximation, you would always have a resistance in series with the inductor coming from the windings, as the windings are typically a piece of wire, which have a material, a conductor material, have a length, and have a diameter, again on its own, so they are as a resistor, as we've previously seen. And then on top of that comes even worse. Every inductor comes with at least, second approximation, at least another capacitor, which is in parallel to the inductor. If you would go and model even more precise, we would actually add even more capacitors to your original inductor that you wanted to buy from your favorite distributor. But you can't get it without the resistance and without the parallel capacitance.